This is Rick and Sarah, and this is the Physics of Basketball, July 2012. The diameter of a basketball hoop is 18 inches, and the diameter of the basketball is only 9 inches. The angle at which you shoot depends on your height and the distance away from the hoop. The closer you are to the hoop, the higher your shot should be. Spinning the ball when you shoot is not done to affect air resistance or to make air resistance cause the ball's path to curve, as is the case in baseball. Basketballs move too slowly for that to happen. Once the basketball leaves the shooter's hands, it travels in an unchanging parabolic path. So what's the purpose of backspin? Backspin on the ball is used to help it bounce into the net when it hits the rim. It will usually hit something unless the throw is very high. The backspin, after contact with the back rim or board, will result in a change in velocity opposite to the spin direction, changing an equal angle rebound into a velocity more toward the net. This makes it more likely that the ball will go in. When the basketball falls to the ground or is dribbled, the ball bounces back. This occurs due to the elastic collision that occurs between the basketball and the ground, or more specifically, the air particles in the ball and the ground. A perfect elastic collision is defined as a collision of particles in a closed system in which the total kinetic energy of the particles is conserved. The elasticity of a basketball can be determined by the height the ball rebounds. The basketball cannot achieve a perfect elastic collision with the ground, but it can, however, achieve as much as 80% elasticity depending on the air pressure inside the ball. The air pressure of the ball greatly affects the elasticity of the ball and the conservation of energy of the ball. A tightly inflated basketball has a large amount of particles present inside the restricted space the surface of the basketball provides. As a source moves towards you, in this case the basketball being dribbled, the waves it creates become compressed, so the frequency you hear is higher than if the source were not moving. While the source is moving away from you, the waves become longer, so the frequency you hear is lower. Isaac Newton's second law of motion deals with the concept of acceleration. Objects will accelerate according to the amount of net force that acts upon them, as well as the mass of the object being accelerated. Since the primary object used in basketball, the ball, provides consistent mass, the only variable from the second law of motion at work is force. Consequently, players must apply varying levels of force for different results. When you apply Newton's first and second laws to your hang time, it means that you will come down to the floor at the same rate you rose from the floor, assuming you don't come into contact with anything. The outside force causing you to come back down to the floor is gravity, which is constant. The resulting force from your takeoff is your mass times your acceleration, or the combined speed and strength you use to launch yourself into the air. This interesting result tells us that half the hang time is spent in the bottom 75% of the jump. The remaining time is spent in the top of the jump. In other words, half the jump time is spent in the highest 25% of the jump, the top part of the arc. This explains why a basketball player appears to hang during the jump. So a player who can jump 4 feet vertically will have a hang time of around a second, with half of a second spent in the high part of the jump.